What is a galaxy? Open up your notes, Milky Way galaxy. What is a galaxy? Well, it could be a spiral, it could be an irregular, it could be a barred. Really, what is a galaxy? There's kind of an artist rendition of ours. What is it? You guys got the notes in front of you? It's really a collection of what? That's under a black hole. Yeah. That's really, kind of in a nutshell, that's what it is. You know, and there are many different types as we went through. We talked about, actually, we didn't get into specifics. I think you had that in middle school, specific types of galaxies. But the parts we want to talk about is that our galaxy is a spiral galaxy, and our solar system / the sun is located where within this galaxy? Third of the way in from one of the arms. Yeah, we're not near the center. We're more on the outer edge. Much of the galaxy is composed not of stars but of clouds. Yeah, what we call nebulas. You know, hydrogen, helium, and some gases. Okay. Notice at the center of our galaxy, it looks really, really what?
Right.
And why is that? There's a black hole there.
Light can't.
Well, I'll agree, not out of a black hole, but that strong gravitational field is going to do what to the nearby stars? Pull them together, so you're going to have a greater concentration of stars. Therefore, you got a greater concentration of brightness. Therefore, it's going to look brighter. Yeah, it's all it's saying there. It's always interesting. And what's the galaxy most like ours? What was the galaxy most like ours called? It's part of the Local group. Well, granted, it's a spiral, but what one? Andromeda. The Andromeda Galaxy is very similar to ours. And we can't see ours because we are what? We're in it. So we're not going to be able to see ours. So really, you're looking at some other ones. The Local group, again, it's somewhat of a loose term. You know, these other galaxies are light years upon light years upon light years away. The other two big ones of the Local group are the Magellanic Clouds. And we can't see those galaxies from the northern hemisphere, but they can pick them up in the southern hemisphere. Anybody been up north or anything, camping or whatever have you? Nice dark night, and you see that what going across the sky? The stars that looks like a what? Hence the term of our galaxy. Yeah, you can actually see the Milky Way. It's a faint glow of stars that's going across the sky. You got to remember, as it's spinning, it's starting to flatten out. So when you see the Milky Way, you're looking into the galaxy. You're not looking out either above or below. You're looking into the center of the galaxy. That's why you see that band of very, very dim stars, but it looks continual because you're looking into it. I did talk about some speeds, some rotational speeds and so forth in that lecture. I'm not going to ask that on the assessment. I won't get into that at all. But needless to say, it is spinning. In fact, looking at this artist rendition, the galaxy looks very similar to a what? Not a tornado, but it looks like a hurricane. That whole idea, when things start rotating, the material starts to form or shape into what? Spiral arms or bands, just like in a hurricane. The clouds form bands. Well, same thing in the galaxies. As they are spinning, they'll start to form bands. So that's probably the big thing. I know you guys talked about the Milky Way galaxy in middle school, so I'm not going to get into a ton of it. But at the middle of our galaxy is that black hole. That black hole. And it is Sagittarius X or Sagittarius A or something to that effect.
Do we need to know
That there's a black hole in the middle?
that? No, what is it?
No, I'm not going to. You don't need to know the name per se, but it is Sagittarius. Any other things to add off that? I think it was fairly short. All right. Okay, open up to the very first page of notes. We're going to go through the review sheet. That review sheet's been up there since Sunday, so hopefully you've availed yourselves to the review sheet. The part where it says be able to calculate the acceleration of gravity on any planet, you're not going to do that on this assessment. You will do it, but it'll be a little bit later in the year, which really isn't. God, what's this, the fourth week already? Later in the year is going to come up pretty quick. Speaking of which, once you guys come back from spring break, if you thought it was a mad rush before Christmas, it's going to be 5 times as worse after spring break. I'm serious. Do not get behind. In the spring, there's so much going on, just with everything, and then weather gets nicer. It's just word to the wise. All right. I know you guys looked at this, but we'll go through it. So, I'm going to kind of start right at the first lecture. What is the Big Bang theory, I guess I should say? Guys, go right to your notes. I'm just going through your notes. What's the Big Bang? Okay. And it's really a theory for the beginning of the universe. And what are the 2 big pieces of evidence for the Big Bang theory? All right, one's that background radiation, and what is it? That's good, you know, you got the name of it, but really, what is it? Or describe it. It's really leftover energy from, and it's, when you look into the galaxy, or look into the universe, it's where? Everywhere at about the same amount. It's just leftover, and it's pretty constant throughout the universe. And we talked about scientists are theorizing that it's leftover from the Big Bang. What is the other large piece of evidence for the Big Bang theory? The what?
Redshift.
And what is the redshift? What is the redshift? The redshift is proof for what? That the universe is what? Expanding. If it wasn't expanding, we wouldn't call it a redshift, we would call it a blue shift. But what really is the redshift? You guys did a whole activity on this. Huh? Yeah, what about a star spectrum? What is a star spectrum? A star spectrum is what? You guys looked at A, B, C, and D. You guys looked at all these other gas tubes. What is a star spectrum? There is reasons we do these activities. You guys look at A, B, C, and D, and we're trying to match up if what were in that star. How soon we forget. What you're trying to match up in the star. Now, granted, it's light, but it's light from what? True. The starlight is composed of, and then I showed gas tubes of specific ones. Elements. You looked at the star spectra, which is really elements that are ionized. And as you went through the spectra, we went through that activity, all those spectra were what? Shifted to the what? The red side of the spectrum, because they are moving out or away from us. So all those elements, all those spectra are shifted to the red side. It's just like in sound. Yeah, you've got the frequency, but if it's moving away, the frequency is lower frequency. Same thing with light. It's moving away, so it looks like it's all shifted to the red side. If it was moving towards us, it would look like they're all shifted to the blue side. That's that whole idea when you guys looked at those stars. There's a couple, 3 questions in there that they were shifted to the red side. Let's see. How was hydrogen produced? What? Hydrogen was produced when? At the Big Bang. Along with some... No, not carbon dioxide then. 2 lightest elements. Helium. Why is hydrogen important? Why is hydrogen important? Hydrogen is important because it's the what for something? The fuel for... Yeah, I got to be more specific. I'll agree, it's the fuel in stars, but it's the fuel for what process? Nuclear fusion. Because during nuclear fusion, what happens? What happens during nuclear fusion? Well, go to that lecture. I'm just reviewing all the lectures and notes you guys took. That's all I'm doing. What happens during nuclear fusion? Hydrogen, 2 hydrogens fuse helium and energy. During fusion, 2 hydrogens will fuse to form helium, but there's a little bit of matter left over. And that matter is converted to what? Energy. That's Einstein. We talked about Einstein's equation briefly. E equals mc squared. M is the mass. And that takes place in the interior of a star, which lends us to what forces are necessary for a protostar to ignite. Gravity, because it's going to start pulling more and more of that dust and gas. And as you get more and more, the gravity increases. As the gravity pulls more and more air, what increases?
Pressure.
As the pressure increases, the byproduct of for higher pressure is greater. Well, if you get them closer together, these particles start hitting one another. Well, the more mass you get, the greater pressure you get. Also, that a byproduct of greater pressure is an increase in, an increase in density will also give you an increase in. It's really what you guys graphed with the HR diagram. Huh? Temperature. The greater the pressure, the greater the temperature. When you get to that point in a protostar where the temperature, pressure, and gravitational pull. Gravity and pressure are the 2 big forces. Temperature is really a byproduct of those. But when you get those 2 forces, you get enough mass there. Once you can get fusion to take place, the sun ignites, or or the star ignites. And how does that energy get from the nucleus or the core of a star to the outer edges? What process gets it out there? Flow of energy. Nothing new here. The flow of energy is referred to as... Come on, guys. You already told me a star is pretty much all gas. The flow of energy through a gas. Starts with a C. We only looked at 3 ways energy is transferred. Huh? Convection currents. I always thought we should have a year-ending exam you got to pass to get out, but have a tendency just to learn it for the moment and then forget it. So yeah, so once that ignites, then you have a star. Our sun's about how old?
3 billion.
Yeah, closer to 5. Our sun's about halfway through its lifetime. It'll burn about another 5 billion or so. The universe about 13.7 billion. So how does somebody give me the lifespan of our sun or any of a star? What do they form from? Well, turn to the formation of the sun lecture. Forms from what? The birthplace stars are really called what? Nebulas. Nebulas are clouds. We talked about those, collection of dust particles, if you will, hydrogen gas and helium. Gravity starts to overtake, starts to clump it. And if you get enough there before a sun ignites, it's called a what? Next stage of the sun's life cycle after the gases start to clump together, it's called a what? I can't hear you. Well, it's not a disk, a protostar. Then it ignites, then it becomes a star. And especially on our sun, the next stage is a red giant. And then from there, it's a planetary nebula. Then from there, it goes to a white dwarf. And then from there, it can go to a brown dwarf. Now, if it's a very, very large star, such as a blue giant, it's going to go to what stage? Supernova. And then it can go either to a black hole, or sometimes what's called a neutrino. So again, the life cycle of a star. We did that already. We already kind of went through a black hole, how it's formed. Can our sun become a black hole? No. We talked about, it's too small. At a minimum, it's got to be 3 solar masses, at a minimum. Our sun, it's only 1 solar mass. Now, if you looked at that stellar evolution poster I've had up there since all year long, typically it's got to be almost that blue giant stage, because you got to have enough mass. If you got enough mass, you've got enough gravitational pull in there. And then it really kind of implodes on itself during that supernova. Doesn't necessarily mean it will form a black hole, but it has a better chance. Let's see. Element production. 2 lightest elements were formed when? At the Big Bang, all right? Our sun forms the elements up to what during its life cycle? Somebody said it? Yep, gets to about oxygen. Bigger stars can form up to what? Somebody said it? Iron. What ends up happening during nuclear fusion, the whole idea that heliums can start fusing together to form other elements, they can fuse together to form other elements. Really, the sun starts cannibalizing itself. It starts fusing heavier and heavier elements, and then it gets to the point where it just can't exist anymore. Our sun will get up to about oxygen. Bigger stars can get up to iron. Elements past iron are formed when or how? The heavier elements are formed during a well, you even got to have more energy. And that energy comes about during a it's right in your notes. It's this whole idea of nucleosynthesis. The heaviest elements are formed during what? During a what? The heaviest elements are formed during a supernova, or it could even be a oh, what's the other one? Supernova and come on, guys. Sun goes from red giant to sun does not form a blue giant. Planetary nebula. Planetary nebula. And during those two stages, you can get the heavier elements being formed. Because you've really got extreme pressure when you get that explosion. So you can fuse even heavier elements to form even heavier elements. What process fuels the sun? We went through that. Stages in the sun's life, we went through that. HR diagram. Vast majority of stars lie on the main sequence. The HR diagram relates what to features of a star? Luminosity and temperature. Luminosity, brightness. Can a white dwarf be very bright? Because it's too small. Now, if it was real close to us, it could, but no. Where's the sun in the HR diagram? Yeah, it's pretty smack dab in the middle, average, and everything's compared to the sun. So that's why it really sits in the middle. But the sun's pretty average. Will the sun spend its whole lifetime on the main sequence? No. It'll move off the main sequence to a red giant. Can a red giant be bright? Yeah, because it's so big. So when you look at the HR diagram, yeah, you're relating temperature and brightness. And I gave you those 4 quadrants. And then the vast majority of stars will be on the main sequence because that's where they live their lives. Oh, you guys did an activity on sunspot cycles. You actually went and graphed that. Tell me kind of the key idea on sunspot cycles. Shouldn't be looking at our computer screens. We should be recollecting our sunspot cycle activity. You guys graphed it. That was probably the most important question on that graph. Sunspot cycle. They cycle through about every 10 to 11 years. You guys graphed this. And as I went through there, you guys most of you had it, about 10 to 11 years. Sunspot cycles also correlate to maximum what? That was the second graph you compared it to. The electromagnetic interference with sunspot cycles. You guys had 2 graphs on that thing. And you looked at those together. One interesting thing on the star spectra, we actually looked at some of those, and we ionized oxygen gas, we ionized nitrogen, I think hydrogen, some others, and they all gave off a different what? You guys looked at them? Color. Yeah, they all look a little different. And it's kind of interesting. This time of year, especially not so much in Michigan, you don't see it, but this time of year, there's a good chance to see the what? You can see the constellations, but the aurora borealis, or northern lights. They're more frequent at the poles or polar regions. Why? Goes back to your middle school science. That's because the magnetic fields of the Earth are the what there? The what? They're close together, so it's the strongest, right? Magnetic field lines are closer together at polar regions. You guys did this in middle school, correct? And that's why, and really, when the sun gets a solar flare, it sends out all these ionized particles out there, and it hits what in the Earth's atmosphere? We did it in class. I just said oxygen, nitrogen, and other gases. It ionizes them, and that gives you your colors of the aurora borealis. It's just ionized gas. But you got to get the energy from the sun there. Well, I guess that was a good survey of your notes from this particular unit. I cannot stress, and again, I've been saying it all year, you need to take the notes, and then we go over it in class. And then you see these things like 5 different times before they even show up. You hear it, you see it, you write it down, we go over in class again, you hear it, and you write anything down that's missing. That's like 5 times. Any questions per se on anything? All righty. I've got no more to add.